So in the last video, we discussed about how to solve linear congruences using the modular inverse. So the modular inverse can be represented with the notation of if a equals 7 here, 7 to the negative 1. Remember, this does not equal 1 over 7. However, this is just the notation. Um, and the definition for modular inverse, or why we find this, is because if we take the modular inverse times 7, which is be a in this case, if you remember the definition of a linear congruence, it'll become congruent to 1 in mod m, or whichever mod we were in for that inverse. So we discussed how to find that modular inverse, and remember, you kind of just, for small numbers, you can kind of just guess and check and start trying different multiples of a against multiples of m. But what do we do when these numbers of a and m get too large to be able to do this? Because at a certain point, these numbers could become so large that guessing and checking would take way too long. Well, luckily, there is an easier method or a quicker method, which we call the extended Euclidean algorithm. So we'll be discussing how to do the extended Euclidean algorithm today and how we can use that to solve linear congruences. Now, this does not solve the linear congruence for us. However, it allows us to find the modular inverse quickly. All right, so we'll go over a couple of examples and let's get into it. If you recall, to know whether or not a modular inverse exists for an equation like this, what we need to do is check that the GCD of A and M equals 1. A modular inverse exists if and only if this GCD equals 1. Now, let's say that A and M are relatively large numbers, difficult enough that we do not want to just guess and check. Then we'll use the extended Euclidean algorithm. And even finding this GCD here might be difficult. So, the extended Euclidean algorithm can be broken up into two parts. The first one is where we find the GCD, okay? And then the second part, find the modular inverse, okay? So, in the first part, we're going to find and check that the GCD equals 1 and that a modular inverse exists. And part 2 is when we actually find the modular inverse. So conceptually, what this is going to look like is we need to know that the GCD of A and M equals 1, right? So we're going to keep doing a process until we get to the value 1. And what that process is going to look like is we're going to take M minus K times A for some integer K such that is in Z the set of all integers. Okay? And this is going to equal, let's call this variable R, which is the remainder of this. And we need K to be some integer times A that gets us as close as possible to M. We need that actually such that the difference of K times A is less than M. Okay? So we're going to start off, this is the very first line we do for the first part. After that, for line 2, what we're going to do is we are going to do A minus R equals, let's say, or we'll have actually K times R. Same concept here too, by the way. Let's say it equals some integer Y, or sorry, no, I'm not gonna do that. It's the same concept here. Now we need k to get us as close to possible as a when multiplied by r. And then we'll keep repeating this process. So we'll do r minus k times y equals, let's just say x here. And we're going to keep doing this process over and over again until eventually we get equals 1 for, let's just say, y minus x. And these variables are hypothetical after r. That'll be the first part. And the second part, actually, let's take that back. In the second part, we're going to work our way back up. So we're going to start with 1 equals, and then here, y minus x. And then just know that it still is a 1 on this side. We'll keep going with that. And then we'll plug in each of these variables. So y here equals this. So we'll do a minus k times r minus, and let's plug in x too. R minus k times y. And we're going to keep doing this, and we're going to eventually be reducing these values until we're left with the linear congruence. This is going to be confusing at first, but it'll start to make sense as you see actual problems. So let's go on to some example problems. So for example 1, we're going to solve the linear congruence where 17x is congruent to 1 in mod 43. Okay, so remember, we need to make sure that the GCD of A, which is 17 in this case, and M, which is 43 in this case, equals 1. Now, these are a bit bigger of numbers, so it'll be a little bit more difficult to do with these. So instead, we're going to do the extended Euclidean algorithm. And we're going to do part 1, where we confirm that that GCD equals 1. So, as I said in the last slide, we start off with 43 minus some k times 17. And this is going to equal some remainder r. So we need to find what k gets us closest there. So if we do this, what do we get? We get 14, 2, 30, we get 34. And I think that'll probably be the closest we actually get here. So we're going to put 2 in as k. And like this ends up giving us, what would you say, that was 34. So 43 minus 34 equals 9. So that value equals 9. Okay. Now, as I said, I'm sorry, we take A minus R in this case. Remember, we're saying that this is A, this is M, and we'll call this R here. Okay, so we're going to do A minus R, which ends up being 17 minus, well, here, minus K times 9 will equal some X. Can we have any multiple K that'll get us closer but not greater than 17? I don't think so, because if we do this, we get 18, that's still greater. So this is just going to end up being 1 here. And I'll leave that there. But you could obviously take this out, because the 1 doesn't really change anything. So 17 minus 9, what does that get us? That should get us 8. Okay. Now remember, we take this value, move it over here. So we get 9 subtracted by this. There technically is some K, but there's no multiple that'll get us any closer. So we're just going to leave it as 8. And what do you know? That equals 1. So since this right here, running this process got us to an equals 1, now we know that that GCD is 1 of A and M. Okay, so now we know that some modular inverse exists. So that's part 1 of the extended Euclidean algorithm. Now I'm gonna erase these parts here just to make this cleaner to look at. Now we need to go in reverse, because now we're on to part 2. I'm gonna clean this up. Part 1. Part 2. Okay, now we need to go in reverse. So we're gonna have 1 equals 9 minus 8. We need to plug in 9 and we need to plug in 8 here. So 1 and then 9, we're taking this right here. So we'll have 43 minus 2 times 17 Is that all in parentheses? Minus 8, which is this right here. So we'll have in parentheses 17, and we'll just make this 9. Okay. Now what we can do is we can simplify this equation. So we'll have 1 equals 43 minus 2 times 17 minus 17 plus 9, because we're factoring this out here. Okay. Now, what can we do here that helps simplify this more is we can combine like terms. So we'll have 1 equals 43 minus 2. Oops, sorry. This will be minus 3, actually. Minus 3 times 17 plus 9. Now, this will end up reducing to 0. However, well, it'll reduce to 0 because we're in mod 43. The remainder of 43 in mod 43 is 0. So that's how we know that reduces to 0. I'm not going to do that yet because we're going to reduce that to 0, but then we're still left with this plus 9 over. So we're going to replug in 9 one more time. So it'll be with 1 equals 43 minus 3 times 17 plus, I guess I don't need that, 43 minus 2 times 17. Okay? Now we can combine like terms one more time. We have 1 equals 2 times 43 minus 5 times 17. Now this is looking a lot cleaner. So let's reduce this to 0 since we said that can happen. We can do that since we're in mod 43. So now we're left with 1 equals negative 5 times 17. And this is getting a bit messy, so let's move this over here. Okay. Now, when you look at this, what I want you to think of is quite literally this definition. Because what is this really saying? It's just saying that a times some number is congruent to 1 in this mod, whatever mod we are in, right? And so when we have this right here, it is saying the same thing, because 17 in this case, remember, 17 is a here. So this would be our a value, and this would be our inverse, negative 5. And since they're multiplied together and it equals 1, it satisfies this definition. So therefore, our inverse is negative 5. Now, I don't really like using negatives as the inverse value because it's kind of, it's a little messy looking, or it doesn't feel exactly right. So to just find what this would be as a non-negative, but the lowest remainder that is not a negative, is we can do 43 minus 5, which will end up being 38. So equals 38. And these are essentially just equivalent. It's just nicer to not have it as a negative. So that is how we do the extended Euclidean algorithm with part 1, where we find that the GCD equals 1, and we're finding what the values of 9, 8, and 1 are in this case. And there'll be different numbers, obviously, for different problems, but we need these because we need these because they're eventually going to plug them in over in part 2 to then find the modular inverse. Okay. And a lot of times with these is you're going to be, plugging in those values and combining like terms. And as long as you have a good understanding of how to reduce in modular arithmetic, you'll be okay. Just sometimes the tricky part could be getting the algebra correctly. So just double check. But yeah, so always just think, how can I plug in and then reduce until you're left with just a value sort of like this. Because then you can recall that it is just like this definition here. Okay, now I'm going to remove this and I'll show you how to solve it again with the modular inverse. So we have the modular inverse equals 38, okay? So let's multiply both sides of this congruence by 38. So we have 38 times 17 times x is congruent to 38 times 1 and mod 43. Okay. This is going to just simplify to 1. So we'll just be left with x is congruent, and this is just 38. The 38 and mod 43. And since 38 is greater than or equal to 0 and less than 43, we do not need to reduce this anymore. And so therefore we found that x equals 38. Okay, to recap, we can use, I'm going to write down short terms, the extended Euclidean algorithm to find a modular inverse. We will use the extended Euclidean algorithm when our a and m values in this become too large to do guess and check to find the inverse, okay? And in the first part, we're just seeing that the GCD of a and m equals 1 in the extended Euclidean algorithm. And in part 2, which is where we do that back substitution, is where we actually find the modular inverse. So when you do these problems, take your time and, recall like you're doing m minus a, k times a equals some remainder. And obviously keep doing this until you find until you find the value 1. If you never find that, then there is no modular inverse. This first part, I would say, is easier than the second part, okay? When you go through the second part, remember that when you find 1, you're putting that very first, in the last example was 9 minus 8, right? Let's just say that this is 9, this is 8. Let's say the next one was 1, where you get this. When you do this part, always remember to substitute in. So it would be like this, minus whatever 8 is here. And you're gonna keep doing this, and I would reduce at the end once you can see that you're left with just the product where 1 is like a times x, or it would look like that. And this will be, you'll be left with the a. So if let's say a equals 17, you'll be left with 17 times some number that'll end up being the modular inverse. That's how you know when it's just this right here, just the multiple equals 1, that you have the modular inverse. So take your time with the substitutions. Make sure to reduce at the end to simplify your problem. And yeah, that's about it to the extended Euclidean algorithm. So thank you for watching. I really appreciate it if you could like or subscribe. If I didn't do that great of a job explaining, I can make another video. Just let me know in the comments, and thank you.